So a polynomial is basically any function that consists of a sum or difference of terms that have real numbers as coefficients and natural numbers as exponents. So what this basically means is that up here you can see the general form of a polynomial. Some people will call it the general polynomial. And these signs between these terms have to either be a plus sign or a minus sign. They cannot be multiplication or division. In addition to that, all of the exponents on x, so all of these numbers here, which we've described as n, they have to be um, natural numbers. And this basically just means that they have to be a positive integer. So, for example, if you had a polynomial that had a term like this would disqualify it from being a polynomial because the n term, or the exponent there, is not a natural number since it's a fraction. So it can't be negative and it can't be a fraction. And in addition to this, the coefficients on each of the terms, the a terms here, these all have to be real numbers. So if you look at this polynomial, you can actually extract quite a bit of information without needing to perform any operations, just at a glance. So just by looking at this, you can identify all of the coefficients. So the coefficients are all of these a terms. They're going to be real numbers that are tacked on to each of the powers of x. So here the coefficients are an minus 1, all the way down until a2, a1, and a0. So this just means here that you can keep, listing terms all the way from whatever this arbitrary n is, all the way down until it eventually reaches 2, 1, and 0. In addition to that, it's important to notice that with this term here, a0 times x to the power of 0 is really just a0. So in an actual polynomial equation, this will manifest as just some constant. You won't usually see the x term written out as x to the power of 0. But again, it's just because x to the power of 0 is equal to 1, so it really becomes this coefficient times 1, which is just the coefficient. So you can also identify the leading term in a polynomial. The leading term will always be the term that contains the highest power of x. Sometimes you might see things written in a different order. It's standard and proper to write it in such an order that the powers of x are decreasing like we have here. So it goes from n to n minus 1 all the way down until it eventually reaches 0. But sometimes it'll be in a different order. So what you want to do is identify the term that contains the highest power of x. So in this case, it's x to the power of n. And then this entire term is the leading term. So in this case, for the general polynomial, the leading term is an x to the power of n. The leading coefficient is simply the coefficient on the leading term. So in this case, if you take a look at your leading term, the coefficient is everything that's not the x to the power of n. So in this case, it's going to be that real number constant that's tacked on to x to the power of n. So in this example, the leading coefficient is an. The degree of the polynomial you can also extract from the leading term. The degree of the polynomial is going to be the highest power of x. In this case, the highest power of x is n. So the degree of this polynomial is n. Additionally, a good rule of thumb is that for any polynomial of degree n, the maximum number of x-intercepts or zeros that it can have is n. So at most, it can have n x-intercepts or zeros. It can have fewer than n, but the maximum number is n. In addition to that, it can have at most n minus 1 turning points. So a turning point would be somewhere where the tangent line has a slope of 0, something like this. And at most, it can have n minus 1 turning points. So it can have less than n minus 1, but it can't have more than n minus 1. And this is going to be true for every polynomial of degree n. So let's go through some examples. So what if I gave you this function right here? Would you be able to identify all of the things that we just pointed out in the previous function? So the first thing to do, a good way to start getting information, is to look for the leading term. So we're going to try to find the term that contains the highest power of x. In this case, the highest power of x is 7. 7 is greater than 3, greater than 1, and greater than 0. So on this n term, kind of like I mentioned before, you can imagine that it's -1 times x to the power of 0, because x to the power of 0 equals 1, so it's usually just not written there. So in this case, we have an x to the power of 1, an x to the power of 0, an x to the power of 3, and an x to the power of 7. So this term contains the highest power of x. So our leading term is going to be 4x to the 7. Then from there, we can extract the leading coefficient pretty easily. It's simply the real number coefficient on the leading term. So in this case, the leading coefficient is 4. Additionally, we can extract the degree pretty easily. It's simply the highest power of x. In this case, the highest power of x is 7, based on our leading term. If we were to list all of the coefficients in this polynomial, we could take a look here. We have 4, -2, +8, and -1. And remember, it's important to include the signs in your coefficients. So be mindful of those. So our coefficients are 4, -2, 8, and -1. And in this case, using the degree, we can also determine the maximum number of x-intercepts that this function can have and the maximum number of turning points. So for a polynomial of degree n, we said that it can have at most n x-intercepts and at most n-1 turning points. So in this case, the degree of our polynomial is 7, which means that at most, it can have 7 x-intercepts, and it can have 7 minus 1 is 6 turning points at most. So this polynomial could have, 7, 6, 5, 4, 3, 2, 1, 0 x-intercepts. And it could have, fewer than 6 turning points as well. I mean, you could see that in this specific case, it actually could not have 0 x-intercepts, simply because 7 is an odd number, and if it has an odd leading coefficient, it has to cross the x-axis to finish in a different quadrant than it started, which means that it could not possibly have 0 intercepts since it needs to cross the x-axis. But in any case, it can have fewer than 7 x-intercepts, and it can have fewer than 6 turning points, but the maximum number is given by this rule over here. So what if I gave you this example right here? This one is a little bit different simply because it's actually written out of order. So a good first step when you see something like this is to try and write it in the standard form with descending powers of x. So we could rewrite this as -x² minus x plus 3. So in this case, this is your final term that has an x to the 0 on it, which is just 1, but it's not shown. And in this case, it's a lot easier to identify the leading coefficient, perhaps, when you have it in order like this. So the leading coefficient is your first, or the leading term is your first term here. So like we did last time, we're going to start by identifying our leading term and getting some information from that. So we have an x to the power of 2, an x to the power of 1, and an x to the power of 0. In this case, the x to the power of 2 is the highest power of x in this function, which means that the term containing this x to the power of 2 is our leading term. So our leading term here is -x to the power of 2. From this leading term, we can extract the leading coefficient. The leading coefficient is the real number that's tacked onto the leading term. In this case, we have -1 times x to the power of 2, which is written like -x to the power of 2. So our leading coefficient, in this case, is -1. Additionally, we can extract the degree from the leading term. The highest power of x in this function is 2, so it is of degree 2. From the degree, we can use the rule that we used previously to determine the maximum number of x-intercepts and the maximum number of turning points. So we know that for a polynomial of degree n, it can have maximum n x-ins, and it can have maximum n minus 1 turning points. So in this case, with n equals 2, we can have 2 x-intercepts and 1 turning point. So we can have a maximum of 2 x-intercepts and a maximum of 1 turning point. And again, if we were to list all of the coefficients, we could just go through and take the coefficients off of each term. So in this case, that would be -1, which was our leading coefficient, another -1 on the second term, and +3 on the final term. So on a closing note, let's go through some examples of functions that may or may not be polynomials, and try to justify why they are or are not polynomials. So first here, we have y equals 5. Do you think that this is a polynomial function? Well, we know that y equals 5 is going to just be a constant. So it's just going to be a flat line that intersects with y equals 5 on a graph. So this function is actually a polynomial function, and that's because it satisfies all of the necessary criteria for it to be a polynomial function. This does consist of a sum or difference of terms that only have real numbers as coefficients. 5 is a real number, and the power of x is a natural number. In this case, kind of like we saw with the last term on a lot of polynomial functions, we have an x to the 0. Y equals 5 is the same as y equals 5 times x to the 0, where x to the 0 is our x term that has as an exponent that is a natural number. 0 is a natural number, and so this qualifies as a polynomial function. We have our coefficient, our leading coefficient is 5. Our degree is 0. So for the second one here, we have y equals the square root of x plus 4 plus 3. So in this case, we can rewrite it like y equals x plus 4 to the power of 1/2 plus 3. In this case, you can already see here, we have this exponent that is not a natural number. In order for something to be a polynomial, it has to be a sum or difference of terms that only have real numbers as coefficients and natural numbers as exponents. So a natural number means it has to be a positive integer. So where this fails is that it's not an integer, it's a fraction. And since there's a fractional exponent, that disqualifies this from being a polynomial. So this is not a polynomial. For the next one, we can similarly rewrite this in exponential form. So we can write this like x minus 2 to the power of -1. Whenever you have a fraction like 1 over x, you can always rewrite it as the denominator to the power of -1, and it will be equivalent. So that's the rule that we use to get it in this form. And here again, we can see it fails the same rule because the exponent is not a natural number. Again, a natural number has to be a positive integer. This time it is an integer, but it fails on this condition. It's not positive, it's negative. And so as a result, this cannot be a polynomial. So for the last one here, we have an absolute value function of x plus 2. And if we were to graph this, the normal absolute value function looks a bit like this. In this case, because of the plus 2, we actually get a shift over to 2 to the left. So it's going to look more like this. So an absolute value function contains the absolute value operation. And if we recall from the definition of a polynomial, it can only consist of terms that are added or subtracted from one another. So the absolute value operation is outside the scope of the definition of a polynomial. And if we were to rewrite this, we could take a look at its behavior a bit more clearly. We could rewrite this like x plus 2 and negative x, sorry, plus 2, which is really what this piecewise function contains and what is graphed here. But in any case, the absolute value function exists outside of the scope of the available operations for a polynomial. And so whenever you have an absolute value expression like this, it cannot be a polynomial.